Let's talk about change of base from Algebra 2B Concepts Lesson 3. Our focus is going to be on using change of base property of logarithms to simplify expressions. So first of all, what's a logarithm? Those of you who watched my video on power properties know what's coming. A logarithm is an exponent. 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 I know it's annoying, but the more times you hear me say it, the more times you repeat it to yourself, the more likely you are to remember that a logarithm is an exponent. In fact, it's the exponent to which a specific base or a specified base is raised to obtain a given value. So it's the exponent 6, this is equal to the exponent 6, to which a specific base 2 is raised to obtain a given value. In this case, that given value is x. So they're saying if you take 2, you raise it to the 6th, you'll get x. By now you're familiar with going back and forth between exponential and logarithmic form. So we know that 2, our base, becomes the base in the exponent. You know that 6 is our exponent, and that x is just the result. Now there's no proper name for the number that goes here, right? We know that 2 is a base, we know 6 is an exponent. This answer does not have a proper name. I call it the result or sometimes the value, but again, that's just my own nomenclature. So properties of logarithms. My, there are many of them. Most of the basic ones kind of mirror what you've seen before with laws of exponents, and by now you've probably given a look and found that when adding logarithms of the same base, yes, they must be of the same base, to get the answer, you multiply the results together. If you're subtracting logarithms of the same base, to get the answer, you take the quotient of the results, and so on and so forth, okay? The tough one, I think, is the change of base property, which can be a little weird and kind of difficult to understand why this is even necessary. So for a change of base, we have A in this case just representing some arbitrary base, and we have B representing the base that's given to you. So let's say you have a base that's greater than 0 and not equal to 1, and then a base B such that B is also greater than 0 and not equal to 1. If you have some logarithmic expression and you want to change to the base, in this case we say, hey, I want to change this to base A, then to do so, you write a numerator of log base whatever you're trying to change to of the result divided by, and in the denominator you have the log, again that's the base you chose, times the original base. So for example, if I had log base 4 of 8 and the question said change this to base 2, you'd rewrite your log base 2, your 8 would go here, and then your original base in the denominator. So that's all there is to it, and we're going to practice it. So let's say you're asked to evaluate log base 3 of 27. Well, what do you do here? Because they didn't say change it to this base, do this, do that, they just said evaluate. Well, here's the trick. As you've been learning, base 10 is the base that we use, right? So the digits 0 through 9, there are 10 of them. We picked base 10 after thousands of years of using different bases. At other times we've used base 2 as the human race, we've used base 20. Now we use base 10 pretty much because you have 10 fingers and that's where the counting resets, and yes, that truly is what it is based on, no pun intended. So in your calculators, because base 10 is kind of the norm, if you push the log button on your calculator and then you would just type in a number, maybe 2 or something like that, it's going to evaluate at base 10 because that's the calculator's assumption. And I would say pretty much any calculator you pick up is going to have that as the default base, and they're not really going to let you use other bases. So most calculators are not advanced enough to where you can pick your base. It's just going to automatically assume that you're using base 10. So that doesn't do us very much good. Or here you see we have base 3. Well, I can't use a calculator on that. So what I'm going to do is I'm going to, step 1, change to base 10. And then step 2, then I can use my calculator to evaluate. Okay? So the whole point of changing to base 10 is to get to a place where I can even use a calculator to help me answer this problem. So if I have log base 3 of 27, let's set this up. So we're just going to do a mirror image, okay? Just piece for piece, we're going to look at my log base 3 of 27, and I'm going to match it to this property. So in this case, they say we take our log, so I have log base 3 of 27, and it's equal to log base whatever. So I'm trying to change to log base 10, so I'll write 10 of, in the example they have x. X in my case is the 27, right? So log base 10 of 27 over log base, again I'm changing to base 10, of, and then they have b, the original base, which in this case is 3. So again, you rewrite log base with the new base you want. So in the numerator and denominator, I wrote log base 10, and then the result was the original result and then the original base. So now I'm in base 10, and I can actually use a calculator on this. So you would grab your calculator, hit the log key. You won't have to type in 10, you'll just have to type in 27, and you'll be able to find that log of 27. It'll probably just look like this when you type it in. Log of 27 is equal to 1.43136, etc. I recommend keeping maybe 4 or 5 decimal places to keep the integrity of the number. If I simplify log base 10 of 3, again typed into your calculator will probably look like that. Log base 3 comes out to 0.47712, etc. So now my simplified number is 1.43136 over 0.47712. I simplify that, and it comes out to 3. So log base 3 of 27 equals 3. So this really wasn't too much work, right? Notice that the main part was just setting this up, translating it correctly using our change of base formula, but from there we were just using a calculator to help us out. Alright, let's do another example. Once again, I'm asked to evaluate, so in this case evaluate log base 4 of 32. I'm going to change to base 10, and then I'm going to use my calculator to evaluate. Alright, let's set it up. So I know I could even write the framework here. I know that log base 4 of 32 is going to have some setup where I have a fraction, log base, my new base, I'm choosing base 10. So you could even write the framework like this, and then just fill in your x and your b, your results and your base. So x in this case is 32. B, my original base in this case, is 4. Now I can use a calculator to evaluate. So log base 10 of 32, I would type into my calculator, and I find that log of 32 is equal to about 1.50515, etc. Again, I kept 5 decimal places. Log 4 is equal to 0.60206, etc. So now I take those two numbers, I take the quotient, and I get 2.5. So log base 4 of 32 is equal to 2.5. In your course layer, pay attention to the digits they ask for. So for example, they might say it around to the nearest tenth, as I did. They might ask for the nearest hundredth, the nearest thousandth, etc. They might ask for a fraction form, so just keep an eye out for that. And again, notice that the bulk of my work was just setting up the problem, so writing the logarithm base that I wanted, and then just being sure to match my result and my base to the numerator and denominator. From there, it was just plugging into the calculator, recording the numbers, and letting that calculator do the work for me. Now, notice that our system, when evaluating logarithms and given no other direction, has been to change to base 10 with the intention of being able to use a calculator once I'm in base 10. So let's do that same way one more time, evaluating log base 5 of 100. So by now we're getting a little more familiar with this. So for log base 5 of 100, I'm going to change my base to 10. So I'll have log base 10 of something over log base 10 of something. In the numerator, I want what was originally the result, so log base 10 of 100. In the numerator, I want my original base, so log base 5. Notice in this case that log base 10 of 100, we can actually solve ourselves, right? 10, because the question is 10 to what power equals 100, so I can solve that in my head, right? It's just 2. So this becomes 2 over log base 10 of 5. Log base 10 of 5 I can't solve in my head. I will have to use a calculator for, and it comes out to about 0.699. So 2 over 0.699, I find that my answer, log base 5 of 100, equals about 2.861. Perfect. Now, let's take a look at a different way to do this. So you saw in my last example that there was a case where I didn't have to use a calculator, I was able to solve in my head. Well, think if we manipulated the base, it just so happened to work out in base 10 that time, but what if I manipulated the base to make this a little bit more easy to do? What if you don't have a calculator? How would you solve it? I'm going to choose my base strategically. So for example, I'm asked to evaluate log base 8 of 16. So when you look at these, think of a number that is divisible into both the base and the result that you're given. So in this case, I would think of 2. Okay? 2 is a good base. So anytime you can use 2 as a base, I recommend it. So instead of changing my base to 10, I'm going to change it to 2, but it works the same way. So I can still set up my problem, log base 10 of, remember in the numerator, we take the result. So in this case, that would be log, oops, I got so used to writing log base 10. Log base 2 of 16. Log base 2 of 16. In the numerator, I write the original base, which was 8, log base 2 of 8. Now notice what I've set up for myself. I can rewrite both of these, just as I did with log base 10 of 100, I can rewrite both of these in exponential form. So log base 2 of 16 is really asking me 2 to the what equals 16. Log base 2 of 8 is really asking me 2 to the what equals 8. Well, I know that 2 times 2 is 4, times 2 is 8, times 2 is 16, so that would be 2 to the 4th power. So if 2 to the 4th power equals 16, then log base 2 of 16 is equal to 4. I know that 2 times 2 times 2 is 8, so if my exponent is equal to 3, that means log base 2 of 8 is equal to 3. Okay? So notice that I was able to solve for both my numerator and my denominator in my head because I chose a base that was computable as far as it had a whole number result. So my answer is 4/3 or 1.3 continuing. Now, this still would have worked had you done it the way we've been doing it, where we use log base 10. So let's do it that way as well. So had I kept log base 10, I would have done log base 10 of 16 over log base 10 of 8. I would have had to use my calculator because 10 to what exponent equals 16? I have no idea. 10 to what exponent equals 8? Again, no idea. So I would have found that log 16 equals 1.2041 and so on. And I would have found that log base 8 equals 0.9031, etc. And when you take 1.2041 over 0.9031, you get 1.3. Okay? So this way, If it's comfortable to you, keep doing it. This way is just kind of fun. It challenges your brain a little bit more. And again, if you don't have a calculator, this first method wouldn't work. Your course player also might ask you specifically to change to a certain base, so it's important to understand how to do that as well. Okay, let's do one more example, and again, we'll write it both ways. So here we are with log base 32 of 8, and we're asked to evaluate it. So again, I'm going to choose log base 2. My general advice would be to check for for bases that are as small as possible. So notice that I could also use a base of 8 or something like that, but again, I'm choosing 2. I like working with multiples of 2. I'm familiar with them, right? 2, 4, 8, 16. I know all the exponents. So again, I'm going to use 2 whenever I can. 3 is another good one to use. 5 is another good one to use. So use any of those smaller prime numbers whenever possible. All right, so let's do this. Let's evaluate log base 32 of 8. This will be our final practice. And I'm going to do it both ways. So let's do it the original way first by using base 10. So changing to base 10 and then evaluating with a calculator. All right. So log base 10 of x is my original result. So log base 10 of 8 over log base 10 of b, my original base, which is 32. So I plug in log 8 into my calculator and I get 0.9031. I plug in log 32 into my calculator. I get 1.505, etc. Now I divide those numbers, 0.9031 over 1.505, and I get 0.6 as my answer. Okay, let's try the other way. So I'm going to choose a base 2. Again, just this is the smallest one, and I'm comfortable with base 2. So I'm going to change these to base 2. So log base 2 of 8, which is the original result I was given, over log base 2 of 32, which is the original base I was given. I can rewrite this in exponential form, okay? So 2 is my base. I'm looking for the exponent, remember, because a logarithm is equal to an exponent, equals 8. So I'm being asked 2 to what power equals 8, and I'm being asked 2 to what power equals 32. All right, so 2 times 2 is 4, times 2 is 8, that's 3 2's. So 2 to the third power equals 8, so my answer is 3. So if I have 8, I multiply by another 2, that's 16, and by another 2, that's 32. So that was 5 2's in total. So 2 to the 5th power equals 32. So I get 3/5. Well, what happens when you take 3 over 5? It's equal to 0.6. Okay, so notice that in either case, my answers were equivalent. So it's okay if you want to practice again this way using base 10 and then evaluating using a calculator. Anytime they don't specify and they just say, hey, evaluate this, feel free to use that method. But there will be times when you are asked to change to a certain base, to simplify a certain way, things like that. So you need to be somewhat familiar and comfortable with this other method as well. So that's it today for change of base from lesson 3.